Paper. There's two warm-up problems to work on before we get started officially here. It's not 310 yet. Should be very straightforward. All right. 311, get started here. So let's find these integrals real quick. They're not too terrible. The integral of 1 over x dx is the natural log of the absolute value of x plus c. The integral is 1 over x squared. If you have 1 over x to a power other than x to the first in the denominator, I would always rewrite it. 1 over x, I like leaving like that so I can recognize the antiderivative is the natural log of the absolute value of x. For anything else, it's good to rewrite it. So I'm going to write this as the integral of x to the negative second power, dx. And then we use the anti-power rule. We get x to the negative first over negative 1 plus c, which I would always rewrite as negative 1 over x to the first. Cool. The reason I'm specifying these two integrals is because we want to look at some improper integrals. So improper integrals. What makes an integral improper? Well, typically that means one of your limits of integration is problematic. And there's actually two types of improper integrals. We'll start with type 1. So type 1 is where one or both the limits of integration are infinity or negative infinity. So for example, the integral from 1 to infinity of 1 over x dx. There's a proper way to do this, and there's a less proper way to do this that still usually turns out right. But the way I imagine your instructors want you to do this is the proper way, meaning we're not just going to take the antiderivative natural log of x and then plug in infinity. It's not really correct. What we're supposed to do here is replace any problem limits of integration, like infinity, later on we'll see some other things, with any letter of your liking. We typically use a B for an upper limit and an A for a lower limit, although really you could use any letter you wanted except for X in this case, because X is already being used. People also use T sometimes or Z sometimes, but I'm going to stick with the convention of using a B for an upper limit and an A for a lower limit, unless there's a reason to do something else. And so we're going to take the limit of that as B approaches infinity. And then we're just going to proceed as usual. We're going to integrate, we're going to plug in, we're going to simplify. And then after we've done all of that, carrying this limit as B goes to infinity throughout the whole problem, then we're going to evaluate them. So we anti-differentiate, we get still the limit as B goes to infinity of the natural log of the absolute value of X evaluated from 1 to B. We then plug in our limits of integration. It's unfortunate that we have a limit and limits of integration, but those are the words we use, so those are the words we use. So we have the limit as B goes to infinity of the natural log of the absolute value of B, although you don't really need the absolute value here because B is positive. It's going to infinity, minus the natural log of 1. And we don't really need to say this, but we might as well point out the natural log of 1 is 0. So then we end up getting the limit as B goes to infinity of the natural log of B. And then I don't really want to write natural log of infinity. I just want to say, as B gets larger and larger and larger, what happens to the natural log of function? Well, it also gets larger and larger, right? Think about the graph. The natural log function, right, does this sort of deal. And even though it does it really slowly, it does get infinitely large as you move further to the right. So this limit is infinite. What that means is the area under the curve y equals 1 over x, which I should have drawn from the beginning, but I kind of forgot. Right, if we look at the area under this curve, starting at 1, even though it doesn't maybe look like it, that area is in fact infinite. And what we're going to say here is that this integral, again, running out of space, but I don't want it, yeah. So I'm going to say that this integral from 1 to infinity of 1 over x dx diverges. You can leave it at that, or if you want to say more, you could say it diverges to infinity. So when we're talking about improper integrals, every improper integral is either going to be convergent or divergent. We're going to say converges if the integral is equal to a finite real number. We're going to say diverges otherwise. So it could diverge to infinity, it could diverge to negative infinity, or it could just diverge because the limit doesn't exist. So let's look at a few more examples. And also, by the way, of course, if you have questions along the way, ask your questions. This is kind of the typical first example. You might have seen it in class already. If your teacher has talked about this, it's usually where people start. But let's look at the other kind of prototypical example, which is the integral from 1 to infinity of 1 over x squared dx. And let me do the graphing part first this time. So I'm going to graph actually both of the functions. I'm going to graph y equals 1 over x, which really I'm just kind of doing a very not specific job of graphing it. So here's your y equals 1 over x. And then smaller than it, at least when we cross the point 1, 1, 1 over x squared gets smaller much faster. So now we're talking about this area under this curve. Oops, sorry, you can't quite see that. Apologies. If you guys can't see something, let me know, please. Same process. We always start off by identifying any problems. Infinity is always a problem. I call them problems. When your limit of integration is something that's problematic, like infinity, we're always going to replace it with an a or a b. So we're going to write that this is the integral from 1 to b of x to the negative second. And we're going to take the limit as b goes to infinity. We already did the integral of x to the negative second, and ended up being negative 1 over x. That's why I did those first two problems. So this is going to equal the limit as b goes to infinity of -1 over x evaluated from 1 to b. We plug in those limits of integration. B first, 1 second, so we get -1 over b minus -1 over 1. I don't think you really need to write, no, let's not write this. So then as b goes to infinity, what happens to 1 over b? Where does it go to? Everybody. 0, right? 1 over a really big number is super duper small. And so this integral is going to equal -1. So this integral converges. So the integral from 1 to infinity of 1 over x squared dx converges, and we would say it converges to 1. And I will point out that it is equally good to just write that this integral is equal. So if you write that the integral from 1 to infinity of 1 over x squared dx is equal to 1, you have said the same thing as I've said right there. Saying that an improper integral equals a finite number includes the fact that the integral must be convergent. There is nothing else you could say if that integral is equal to a finite number. Correct. I say diverges. I only say diverges to infinity if it specifically diverges to infinity. So the area under the curve could be negatively infinitely large, and I would say it diverged to negative infinity, or it could not have a particular value. Let me show you an example of what I mean. Let's say someone's gave us this kind of unfortunate integral. The integral from 0 to infinity of cosine of x. Which I guess you could graph, but it's not super helpful, right? If we graphed it, we know what cosine looks like. It's this kind of thing where you've got this sinusoidal function. It just keeps on doing this. So we've got that area minus that area plus that area minus that area plus that area minus that area forever and ever and ever. It wouldn't be unreasonable to guess that the answer might be 0, because you could kind of maybe convince yourself that those areas cancel out. They don't, unfortunately, or at least they don't in a way that we mathematically say it does. Doing this the right way, let's see what happens. So infinity, I have to replace it with a b or whatever letter we like. So I've got the limit as b goes to infinity of the integral from 0 to b of cosine of x dx. And then we're going to get the limit as b goes to infinity. The antiderivative cosine is positive sine of x from 0 to b. We plug in, we get the limit as b goes to infinity of sine of b minus sine of 0. Sine of 0 is 0. And now let me ask you, thinking about what the sine function looks like. As you go further and further to the right, as b goes to infinity, what value does sine get closer and closer to? It doesn't. It keeps going back and forth between 1 and -1, 1 and -1, and all the values in between. But this limit as b goes to infinity of sine of b doesn't exist. This function doesn't get close to one specific finite value as we move further and further. Someone have a question on Zoom there? Let me mute them. I have that power. If you need to ask a question, though, you're welcome to ask a question. Just let me. So this limit does not exist. So we see that this integral from 0 to infinity of cosine of x dx diverges. But I want to be specific here. It doesn't diverge to infinity. Right? We're not getting an infinite amount of area. It doesn't diverge to negative infinity. It just diverges. And that's all we can say. Cool. Let's look at the, oh yeah.
Why can't we say
You might be able to get away with saying that, but I don't know if you could really. Yeah. It's potentially possible, but the thing is to converge, it has to get close to one value. It can't be, but the thing is, this is going to keep going back and forth, maybe between 1 and -1 or something like that. But again, that's not specific enough for us. So yeah, I like the way you're thinking. That's not a bad idea. All right. So let's look at another example, which I think is useful. So this next example is going to come back in 21C when you start talking about series, whether or not a series converges, and talking about the integral test. But for now, I just want you to remember this example later on. So far, we have the following. The integral from 1 to infinity of 1 over x to the first diverges. And the integral from 1 to infinity of 1 over x to the second converges. What about the integral from 1 to infinity of 1 over x to any power? Or I should say, really, what about this integral? That's not really phrased. I should really say, sorry, for what values of p does this integral converge or diverge? Well, let's do it. Oh, question. Oh, okay, well, we're gonna work through the answer, but so I will point out that 1 is kind of the cutoff. So being bigger than 1 is going to lead us towards convergence. Having a power that's less than 1 is going to lead us towards divergence, less than or equal to 1. You kind of see, right, if your power is bigger than 1, your 1 over x of that power is going to get small fast enough so that the area under that curve is finite. Whereas if it's not smaller than 1, if it's bigger than, or sorry, if it's not bigger than 1, it's not going to get small. But let's actually do the work. So we do the integral from 1 to infinity of x to the negative p. We're going to write that as the limit as b goes to infinity of the integral from 1 to b of x to the negative p. We're going to anti-differentiate. We're going to get x to the negative p plus 1 divided by negative p plus 1 from 1 to b. And then we're going to look at two different cases. We're going to look at that case where that power is positive and where that power is negative. And we're not going to worry about that power being 0 because we already dealt with that case. If that power were 0, p would have had to have been positive 1. And we already dealt with the case where p was positive 1. That integral diverged. So case 1, negative p plus 1 is positive. Or in other words, 1 is bigger than p, or p is less than 1. So if p is less than 1, well, that power is positive, right? That's what we just said. So then the limit as b goes to infinity of b to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. Well, 1 to any power is 1. And again, we actually don't really care about this finite part. I mean, we do care if it converges because then it'll converge to that number. But let's focus on this for a second. Negative p plus 1 is positive. B is getting infinitely large. Infinity to a positive power is still infinitely large, even if it's a small power. Like infinity to the 1/2, or the square root of infinity, still infinitely large. Infinity to the 1/1,000,000th power is still going to get infinitely large. So as long as you have infinity to a positive power, it's going to grow to infinity. So we're going to get infinity minus something that's finite, it doesn't matter. So in case 1 here, where p is less than 1, we get divergence. And then technically, I should really say p less than or equal to 1, because we saw before that if p was equal to 1, that interval diverged as well. On the other hand, in our second case here, case 2, if negative p plus 1 is less than 0, then that means that p is greater than 1. So if we rewrite this, the limit as b goes to infinity of b to the negative p plus 1 over negative p plus 1 minus, I'm just going to write 1 over negative p plus 1 because I know that 1 to any power is just 1. Well, I'm going to rewrite this so that my power is positive, because if I write it this way, my power is negative, right? Negative p plus 1 is negative. So if I rewrite this as the limit as b goes to infinity of 1 over b to the positive p minus 1 times negative p plus 1 minus 1 over negative p plus 1. P minus 1 is positive because p is bigger than 1. And infinity to a positive number is infinitely large. And 1 over something infinitely large is getting smaller and smaller. So this one ends up converging to negative 1 over negative p plus 1, which I would write as positive 1 over p minus 1. So if p is bigger than 1, we get convergence. So let's actually write that over here just so we can say it again. The integral from 1 to infinity of 1 over x to some power converges if that power is bigger than 1, diverges if that power is less than or equal to 1. What's nice about this is it can give us some intuition as to whether or not something's going to converge or diverge. For example, I like this example. If I was going to do the integral from 2 to infinity of 3x squared over the square root of x cubed plus 1. I can't exactly use this, but I can think to myself, well, I essentially have an x squared divided by an x to the 3 halves. This function here is really acting like x to the 1/2 power in the numerator, which means I'm definitely thinking I'm getting divergence here. I can use a u substitution. U is x cubed plus 1. My du is going to be 3x squared dx. I know in the past, I've usually said I think it's a good idea to change your limits of integration when you do a u sub. This is an exception to that. When it's improper, I would usually not change my limits of integration. I would do the indefinite integral first and say that the indefinite integral of 3x squared over the square root of x cubed plus 1 dx is equal to the integral of du over the square root of u, which is going to be the integral of u to the negative 1/2 du, which is u to the positive 1/2 divided by 1/2. And then we're going to get 2 times the square root of x cubed plus 1. I would do all that on the side and then go over here and say, okay, then my improper integral is going to be the limit as b goes to infinity of the integral from 2 to b of 3x squared over the square root of x cubed plus 1 dx. And then I would jump straight to saying, well, great, I know the antiderivative of that is just 2 times the square root of x cubed plus 1. This is going to equal the limit as b goes to infinity of 2 times the square root of x cubed plus 1, evaluated from 2 to b, and then we plug in our limits of integration. We get the limit as b goes to infinity of 2 times the square root of b cubed plus 1 minus 2 times the square root of 2 cubed plus 1. And then since b is going to infinity, b cubed is also infinitely large, and the square root of that is also infinitely large. This is definitely diverging to infinity minus 2 times the square root of 9. I guess I don't really care what that is. That's still infinity. This is diverging or divergent. We haven't done anything with negative infinity yet. Let's do one with negative infinity. Yeah, sure. Let's do this one. What about the integral from negative infinity to positive 1? Yeah, positive 1. I like positive 1, sure. Of the 2x over x to the fourth plus 1. So I'm pretty confident this integral is convergent, and here's why. If I think about just my highest powers of x for a second, this integral is similar to the integral of x over x to the fourth, which is 1 over x cubed. And my p is definitely larger than 1, so I'm thinking this is going to converge. And there is something called the comparison test we could use to show it converges, but this one we can actually find what it converges to. But it's a little bit tricky. So there is a u sub here. It's a bit of a guess, but does anyone want to venture a guess as to what might be a good choice for you? It's not immediately obvious. It's okay if no one's great. So here's how I'm thinking about what I want to choose for you. I don't want to pick x to the fourth plus 1 because the derivative of that is 4x cubed. I want to pick something for you whose derivative is already there. I see a 2x being there. What thing has a derivative that is equal to 2x? Yeah, x squared. And x squared is an excellent choice here because then the x to the fourth in the bottom will become x squared squared, which is u squared. So we're going to say that du is, oh, lovely, 2x dx. That's great. And then my x to the fourth plus 1, well, the x to the fourth is really u squared because of x squared squared. So this is going to become the integral of du over u squared plus 1. And I think we've seen quite a bit of this lately. What's the antiderivative of 1 over u squared plus 1? Everyone's favorite, arctangent of u. So this is going to be equal to the arctangent of x squared. Okay, so then going back to the actual improper integral. Improper? Proper, yeah, sorry. That's the right word, right? That's what we said before. Sorry, I'm like losing my mind here. Improper, right? Yeah, improper. Sorry, sometimes there are words that like just get messed up in my brain. Okay, improper. So going back to the actual improper integral from negative infinity to 1 of 2x over x to the fourth plus 1, we're going to write this as the limit as a approaches negative infinity of the integral from a to 1 of 2x over x to the fourth plus 1. We just did the antiderivative of that, so we're going to get the limit as a goes to negative infinity of the antiderivative, which was the arctangent of x squared from a to 1. We plug in and we get the limit as a goes to negative infinity of the arctangent of 1 squared, which is 1, minus the arctangent of a squared. Now I said I was pretty sure this was going to converge. What's arctangent of 1? Tangent of what angle equals 1? Pi over 4. What's the limit as a goes to negative infinity of arctangent of a squared? Or in other words, what's the arctangent of a really, really big number? It's not a really big number. It's less than 2. So this comes up, unfortunately, more often than we would like. But I'll remind you that the way we got the arctangent function was by taking the tangent function and interchanging x and y, which essentially takes your tangent graph, which I'm just going to draw a little bit of it here, the tangent graph from negative pi over 2 to pi over 2, where we have vertical asymptotes. Tangent looks like this. So the inverse tangent graph, or the arctangent graph, you take that graph and you flip it or reflect it across the line y equals x, essentially interchanging all the x things and the y things. That's what happens when you interchange y and x. So instead of getting vertical asymptotes at negative pi over 2 and pi over 2, we're going to get horizontal asymptotes at pi over 2 and negative pi over 2. And the graph looks like this. So if the argument of the function is getting very, very positive, going to infinity, then the actual arctangent function itself is getting closer and closer and closer to positive pi over 2. If the insides of the arctangent function were going to negative infinity, then the values would be getting closer and closer and closer to negative 2. In this case, even though a is going to negative infinity squared is positive big number, and arctangent of positive big number is positive pi over 2. And since we're subtracting it, it's subtracting positive pi over 2. And then pi over 4 minus pi over 2 is negative pi over 4. Which if you graph this function would be sensible because the area under the curve is going to be mostly negative. Kind of weird. Yeah. Go ahead. So the arctangent function is essentially undoing what the tangent function does. So what we're saying here is that y equal to tangent of x is equivalent to x equal to the arctangent of y. Sorry, I keep wasting it. So we know that 1 is equal to tangent of pi over 4. And the square root of 3 is equal to tangent of pi over 3. And tangent of pi over 6 is equal to the root 3 over 3. And those all correspond to the let me write it the right way, to pi over 4 equaling the arctangent of 1, or pi over 3 equaling the arctangent of root 3, or pi over 6 equaling the arctangent of root 3 over 3. When I read this function, when I look at this arctangent of 1, the words that are actually being said in my brain are find the angle, emphasis on angle, whose tangent is equal to whatever number is in there. In this case, 1. So what's the angle that if I take tangent of that angle, I get 1? Oh, it's pi over 4. And this is where your knowledge of the unit circle has to kind of be there. Or you can just leave it as arctangent. That's also not unacceptable, but usually people are going to expect that. I should say it's not unacceptable, but it might be unacceptable. People are going to expect that you do simplify arctangent of 1 or root 3 or root 3 over 3. Or I guess 0 as well. Arctangent of 0 is 0. Tangent of 0 is 0. Okay, so let's look at one more example in this genre, and then we'll talk about the type 2s. Do I have enough room here? It's debatable. Let's not. Let's look at this. What if both limits are either infinity or negative infinity? Like the integral from negative infinity to infinity of x cubed e to the negative x to the 4th dx. So a good rule of thumb with these improper integrals is you can only deal with one problem at a time. So if your improper integral has 2 problem limits, you have to break it up into 2 integrals, or essentially an integral for every problem. So if there were 3 problems, which there could be when we start talking about type 2, you have to break it up into 3 integrals, which is kind of terrible. So you can break this up anywhere in between negative infinity and infinity, which is literally any real number you like. The typical choice is 0, unless there's a good reason to pick something else. So we're going to write this as the integral from negative infinity to 0 of x cubed e to the negative x to the 4th dx, plus the integral from 0 to infinity of x cubed e to the negative x to the 4th dx. And since I can see that the anti-differentiation of this function is going to require some sort of process that's a little bit more complicated than just being direct, I'm going to do the indefinite integral before I actually look at the improperness. So just doing the antiderivative of x cubed e to the negative x to the 4th dx, I'm going to try a u sub. I'm going to let u equal a negative x to the 4th. My du is going to be negative 4x cubed dx. I'll do this one the way I don't usually do it, where people like to isolate dx. It's not my jam, but some people like it. So I'm going to say dx equals du divided by negative 4x cubed. And then I'm just going to replace just dx. So this is going to be the integral of x cubed e to the negative x to the fourth times du over negative 4x cubed. Whenever you do this, your first thing to do immediately is to cancel, if you can, whatever is in that denominator there. And then we replace everything that's left. So then we're going to write this as negative 1/4 times the integral of e to the u du. The integral is negative 1/4 e to the u. I'm not worrying about the plus c here because I'm just doing this for my own knowledge. Right? They didn't actually ask me to do this indefinite integral. So then I'm going to get negative 1/4 e to the negative x to the fourth. That's my antiderivative of x cubed e to the negative x to the fourth. Great. Now we're going to deal with the improper integrals. So let's deal, and so here's what we usually do. Deal with them one at a time. If one of them diverges, you stop, you're done, the whole thing diverges. Doesn't matter what the other half or the other piece does. Which is there, we'll get to in a second how sometimes that's a little disappointing, but okay. So here, I'm going to deal with the one that looks nicer first, the one with infinity, just because I prefer positive numbers over negative numbers. What can I say? So we're going to look at the limit as b goes to infinity of the integral from 0 to b of x cubed e to the negative x to the fourth dx. But we know when we do this, we're going to get exactly negative 1/4 e to the negative x to the fourth. So it's going to be the limit as b goes to infinity. I'm going to skip a step. Instead of writing this evaluated between 0 and b, I'm just going to plug in the b and plug in the 0. So I'm going to say that that's the limit as b goes to infinity of negative 1/4 e to the negative b to the fourth minus negative 1/4 e to the 0 to, or negative 0 to the fourth. I should just write 0. Because negative 0 to a power is still just 0. Okay, we have to be a little bit extra careful here. B is going to infinity. B to the fourth is also infinitely large. So you have an e to a negative infinity. What happens with e to the negative infinity? Does it get big or does it get small? Think about the graph of e to the x. If you go way to the left, it's going to get small. If you don't like this, and I don't love e to the negative infinity going to 0, you can alternatively try to make your power positive and write this as the limit as b goes to infinity of negative 1/4 times 1 over e to the positive b to the fourth plus 1/4. And then for me personally, it's easier to see that b to the fourth is infinitely large, e to the infinity is still infinitely large, and then 1 over that is going to be infinitesimally small. I like that better, but either way will get you there. So this portion of my improper integral converges to 1/4. Now we have to do the other. So if the first piece converges, you then do have to go look at the second piece and see if it also converges. If either piece is divergent, the whole thing is divergent. If all the pieces are convergent, then the integral is going to converge to the sum of those convergent pieces. So luckily, we've already done most of the work. We look at the other half. We're going to do the limit as a goes to negative infinity of the integral from a to 0 of x cubed e to the negative x to the fourth dx. That's going to be the limit as a goes to negative infinity of, we're plugging in 0 first this time. So it's going to be negative 1/4 times e to the 0 is just going to be negative 1/4 minus negative 1/4. Let's make that a plus 1/4 e to the negative a to the fourth. Okay, here's where it's easy to get it wrong. That exponent there is going to negative infinity. Excuse me. Negative infinity to the fourth power is positive infinity, and then the negative of that is negative infinity. Right? The exponent happens before the negative. PEMDAS or whatever people, right? Please excuse my dear Aunt Sally. Right? We do the exponent first and then the negative after. So this is an e to the negative infinity, which is going to go to 0. So we end up with a negative 1/4. So the whole integral converges to what? What do those two pieces add up to? Yeah. Feels kind of disappointing that it converges to 0, I feel like, but it does. So the end result here is that the integral from negative infinity to infinity of x cubed e to the negative x to the 4th dx converges to 0, or is equal to 0. Now, if we had noticed that that function inside the integral was an odd function, it might not be so surprising that that integral is equal to 0. Because generally, the integral from negative a to a of an odd function is equal to 0. And now for the disappointment. Here's the disappointment. I mean, you might disagree. I feel like this is a disappointing fact. What about the integral from negative infinity to infinity of x cubed? Which kind of looks like this. Here's your x cubed. You're essentially saying it's all this area minus all that area. Wouldn't it be nice if it was equal to 0? It would be nice, but it's not. So here's the deal with improper integrals. You have to deal with one piece at a time. You can't deal with two problems at once. And once one piece diverges, stop, you're done. The whole thing diverges. So for this one, if we write this as the integral from negative infinity to 0 of x cubed dx plus the integral from 0 to infinity of x cubed dx, and we look at either piece, let's do this piece. The integral from 0 to infinity of x cubed dx is equal to the limit as b goes to infinity of the integral from 0 to b of x cubed dx. We get the limit as b goes to infinity. The antiderivative of x cubed is x to the 4th over 4. And then we evaluate from 0 to b. We plug in b. We have the limit as b goes to infinity of b to the 4th over 4 minus 0 to the 4th over 4 is 0. And then as b goes to infinity, b to the infinity, or b to the 4th goes to infinity as well. And this ends up being infinity. And the whole thing diverges. So we say that this integral from negative infinity to infinity of x cubed dx diverges. We would not and could not say it diverges to infinity. Because if we did the other half of it, the other half would diverge to negative infinity. And the problem is that infinity plus negative infinity, or infinity minus infinity, is an indeterminate form. It's not necessarily 0. It could actually be anything. And that's why we can't say that this integral is equal to 0, even though there's a lot of people that would really like to, myself included. So if an integral, if you have an improper integral from negative infinity to infinity of an odd function, if that integral converges, then it will converge to 0 because of odd function properties. But if it's divergent, then you're out. It's just divergent. Okay. Let's look at some other examples. I should say, let's look at type 2. So type 1 is when one or both of your limits of integration are infinity or negative infinity. They can't, and when I say both, I mean one is negative infinity and one is positive infinity. Right? You can't have both. You could have both being infinity, but that wouldn't be very sensible. The other type, the type 2, is when your function you're integrating is undefined somewhere in your interval of integration. So just as an example, the integral from -1 to 2 of 1 over x squared is improper. And I will point out, you should not write down the thing I'm about to write down. If I was to do this the wrong way, I know that the antiderivative of 1 over x squared is -1 over x from -1 to 2. If I plug in, I get -1/2. -1/2 minus -1 over 1. It ends up being -1/2 plus 1, which is 1/2. But if you look at the graph, 1 over x squared looks like this. If I go from -1 to 2, I think the area under the curve there, I think that's a lot more area than 1/2. I mean, specifically, the area of this little portion right here, that is a square whose base and height are 1. The area of that square is 1. So this is not right. So all of this is wrong. And the reason it's wrong is because we ignored the fact, or we didn't observe the fact that 1 over x squared is undefined when x is equal to 0. And 0 is in that interval of integration. I should point out, this integral is improper. On the other hand, the integral from 2 to 7 of 1 over x squared is totally just normal, right? This is not improper. This is proper. And you can say it's equal to -1 over x from 2 to 7 and get -1 over 7 minus -1 over 2, which is some terrible fraction. 1/2 minus 1/7. That would be fine. So these ones are sneakier, right? You have to actually be like, okay, well, I've got some function that might be undefined somewhere. I have to think about, is that function undefined on the interval that we are integrating over? This one is. Where is it undefined? 0. Since 0 isn't one of the actual limits of integration, we have to break this up at the point that's a problem. So we're going to rewrite the integral from -1 to 2 of 1 over x squared dx as the integral from -1 to 0 of 1 over x squared plus the integral from 0 to 2 of 1 over x squared. And then just like with the previous problems where we had an infinity and a negative infinity, we broke it up into 2 integrals. We're going to deal with each integral separately. And really what we're going to do is we're going to deal with one at a time. If one of them is divergent, we stop, we're done, the whole thing diverges. You never need to check the second piece if the first piece diverges, unless you are specifically asked what the integral diverges to. So I'll address that in this problem. So let's look at this piece first. So that piece there, I'm going to write as, now watch this, there's something a little extra special that happens here. The limit as b approaches 0 of the integral from -1 to b of 1 over x squared. And the special thing that I haven't written yet is that we actually want to write that it's the limit as b approaches 0 from the left-hand side. If you're between -1 and 0, you're on the left-hand side of 0. So we approach 0 from the left. For the other one, we're going to approach 0 from the right. More generally, if the thing you're replacing is an upper limit of integration, you're always approaching it from the left. If the thing you're replacing is a lower limit of integration, you're always approaching it from the right. We don't ever write that for infinity and negative infinity because you're obviously approaching infinity from the left-hand side. You can't approach infinity from the bigger than infinity side of infinity. And you can't approach negative infinity from the less than negative infinity side of negative. So we never write those things for those. But for these ones, we do. So then we're going to do our usual thing. We have the limit as b approaches 0 from the left. We anti-differentiate. We've seen the antiderivative of 1 over x squared enough times to know that it's going to be -1 over x from -1 to b. We plug in. We get the limit as b goes to 0 from the left of -1 over b minus -1 over -1. So we end up getting -1 over 0, which is divergent. And specifically, it's a -1 over a slightly negative number. So that's going to blow up to positive infinity because it's a negative over negative. So you get infinity minus 1, which is infinity. And if we were only asked about the behavior, at this point we could say diverges, end of story. If someone was cruel enough to ask us, what does that diverge to? We would then have to look at the other piece. And if we did that, the other piece would also diverge to positive infinity. The limit as a approaches 0 from the right of the integral from a to 2 of 1 over x squared. Showing not a lot of work here is going to be the limit as a approaches 0 from the right of negative 1 over 2 minus negative 1 over a. As a goes to a slightly positive number, negative 1 over a is 1 over a, which is 1 over a very, very small positive number, which is going to go to positive infinity. So we end up getting negative 1/2 plus infinity, which is infinity. So we could say, if we had to, that this entire integral diverges to positive infinity. I will also point out, if this had been an infinity and a negative infinity that were added together, all we could say is it diverges. You can't say to what if one piece is infinity and another piece is negative. Okay. So whenever we're looking at an integral, some people are nicer about this than others, but someone might just ask you a definite integral, and it might be your job to recognize whether or not it is improper or not. Whereas on some people's tests, they're like, here are some improper integrals, deal with it. So read your test carefully. If you have definite integrals on your exam, which you probably will, if they don't say anything about improper versus proper, then you should be checking to make sure, like, is that function undefined somewhere on my interval of integration? Like this next one, which I think is a little tricky to see. So the next integral, the integral from 0 to pi of sine of x over 1 plus cosine of x. That function is undefined. I should say the function, which is the integrand, sine of x over 1 plus cosine x, that integrand is undefined when x is equal to pi. Because cosine of pi is equal to -1, and 1 plus -1 gives me a 0 in the denominator. So we're going to rewrite this as the limit as b approaches pi from the left-hand side of pi, integral from 0 to b of sine of x over 1 plus cosine of x. And then I guess we have to do a u substitution. Do we have to do a u substitution? Yeah, that's the best way to do it. There are other ways you can do it. U sub is the best here. So on the side, we're doing a u equal to 1 plus cosine x. My du is negative sine x dx, so a negative du is a positive sine x. So my indefinite integral of sine x over 1 plus cosine x is equal to the integral of negative du over u, which is going to be the negative natural log of the absolute value of u, which is going to be negative natural log of the absolute value of 1 plus cosine x. So then over here, we can say this is going to equal the limit as b goes to pi from the left of the negative natural log of the absolute value of 1 plus cosine of x from 0 to b. And plug in, we get the limit as b approaches pi from the left of negative natural log of 1 plus cosine of b minus the negative, so let's minus and minus, plus the natural log of 1 plus cosine of 0. Okay, these ones are always a little tricky. Cosine of b, well, if you plug in pi, we're going to get 1 plus cosine of pi, which is -1. 1 plus -1 is 0. And the natural log of 0 does what? It's where it's really good to have a graph of natural log of x sitting in your head. If you think about the x values getting closer and closer to 0, with the natural log function, the y values are going down, down, down to negative infinity. Because your y equal to the natural log of x graph looks like this. So as the x values get closer and closer and closer and closer to 0, the y values go to negative infinity. So here we're going to get negative infinity plus the natural log of 2, which is just going to be infinity. So this integral diverges to infinity. They don't all diverge, but these first two do. Have okay. Have hope. I mean, there's nothing wrong with being divergent. It just always feels like, I don't know why, but to me, it's always felt like we would prefer it if an integral converged. I have no idea why I feel that way. Maybe it's just me, but like it just feels like I want that integral to converge. It just feels better. Feels like the integral has failed to live up to some metric that doesn't. So let's look at another example. This is fun. Integral from 1 to e of 1 over x times the square root of the natural log of x dx. And if you weren't looking super carefully, you might not notice where this integral is improper. But it definitely is. If you plug in 1, the natural log of 1 is equal to 0. And that's going to be a problem because you're going to have division by 0. So we're going to rewrite this as the limit as a approaches 1 from the right-hand side. The integral, okay, good. I always forget that the chat's like not up. So let's see if I'm good. Okay. Sorry, the limit is a approaches 1 from the right of the integral from a to e of 1 over x times the square root of natural log of x dx. Just to be super clear, I know no one's asked, but I'm gonna say anyway. There's a way I know that I'm approaching 1 from the right is if I think about my interval of integration from 1 to e. Well, if I'm between 1 and e, I'm obviously on the right side of 1. So that's why I get to say a is approaching 1 from the right, because we're not on the other side. So, u substitution, we're going to let u equal the natural log of x. Du is 1 over x times dx. So the integral of 1 over the square root of natural log of x times 1 over x dx, which I definitely rewrote a little bit to make it more obvious what my du was. There's my du. There's my u. So I have the integral of 1 over the square root of u du, which is the integral of u to the negative 1/2, which is u to the positive 1/2 divided by 1/2, which is multiplied by 2. So then we get 2 times the square root of the natural log of x. So that's what our antiderivative is here. So then we take this here and we say that that's going to be equal to the limit as a approaches 1 from the right, and the integral of 1 over x root natural log of x is exactly 2 times the square root of natural log of x. Evaluated from a to e. Reminder, a is a real number. Sorry. Reminder, e is a real number, and a is just a placeholder for. So this is the limit as a approaches 1 from the right of 2 times the square root of the natural log of e minus 2 times the square root of the natural log of a. And then if you can just plug in your value for a and get a real number, we should. So I'm going to plug in a equal to 1, and we get 2 times the square root of the natural log of e is 1. 2 times the square root of the natural log of 1, that's just 0. So we end up with 2. So this integral converges. Okay. Questions about any of these things we've done? I got a couple more examples for you, but I just want to take a moment to see if there's anything that seems confusing or something I might need to address. All right. Yeah. So, oh yeah, I don't say it. Yeah. I don't want to do this next one, but I want to point out that if someone gave you something atrocious like this, this one's really gross. How many problems are there? Or let me ask a better question. What values of x are problematic? What's one of them? One's a problem. Oh, you picked the hardest one, I think. The other two are right there. Is infinity a problem? Always. Is zero a problem? For sure. For actually both pieces, right? Divided by zero and natural log of zero, both issues. So here, x equals 0, x equals 1, and although I don't like to write it, x equals infinity are all problems. And you can only deal with one problem at a time. So if you were going to do this integral, you'd have to break it up like this to start and break it up at the problem point. I'm just going to write f of x for my function. But each of these integrals both have both limits of integration as problems. You'd have to break each of those up again. So you'd have to write this as like the integral from 0 to pick any number you like between 0 and 1. I'm going to pick 1/2. Plus the integral from 1/2 to 1 of f of x. Plus the integral from 1 to any number between 1 and infinity. I'm going to pick e because the natural log of e is nice to find. That might not be the u. You can pick anything though. You can pick 2 or 5 or 1,000,000. So that's how we would have to break this up to begin approaching doing it. Now, here's a good word of advice. If you have multiple pieces, you should try to do the one that you think is going to diverge. Because if it diverges, you don't have to do any of the other ones. So if we look at the integral here for a second, we are actually going to do this one. It's just, we're not going to do all of it. So I'll point out that the antiderivative of 1 over x times natural log of x squared, most of these, a lot of these end up being u subs. U equals natural log of x, du is 1 over x dx. This becomes the integral of 1 over u squared, which is going to be negative 1 over u, which is going to be negative 1 over natural log of x. So many of these values are going to be problematic for that. Infinity actually won't be. Negative 1 over natural log of infinity will go to 0. So this is probably the only one I shouldn't pick. Because if I pick that one, it's going to converge, and then I'm going to have to do something else. So let's pick one of these ones that might diverge. I'm going to do any of them diverge? No, yeah, okay. So some of them, one of them does diverge. Let's pick this one. So here's what I'm doing to assess if I think it's going to diverge. I'm plugging in the endpoints to this function. Here, I was going to do that one, but then I realized that if you plug in 0, natural log of 0 actually goes to negative infinity, and a 1 over an infinity is going to converge to 0. So that's actually not a good choice. I'm going to pick that one because natural log of 1 is 0, and division by 0 is going to yield divergence. So if we do that one, the integral from 1 to e of my 1 over x natural log of x squared dx is going to be the limit as a approaches 1 from the right of the integral from a to e of 1 over x natural log of x squared dx. We get the limit as a goes to 1 from the right. If we integrate this, we get negative 1 over natural log of x, evaluated from a to e, and then we plug in, we get the limit as a approaches 1 from the right of negative 1 over the natural log of e minus negative 1 over the natural log of a. And the 1 over natural log of a here, since a is going to 1, natural log of a is going to be 0. That's going to be a 1 over 0, which is going to go to infinity. So this part here goes to infinity, so we get divergence. Because once one piece diverges, the whole thing diverges. So if you have multiple pieces, it's a good idea to try to pick the piece that you think diverges. Let me actually show you another one, which we're not going to do, but I want to point out what you would do. So, yeah. Let's say we had the integral from negative infinity to infinity of, let me make sure I get this right, x squared e to the x cubed dx. E to the negative x cubed. That's a little bit more fun. We'd obviously have to break it up. So it's the integral from negative infinity to 0 of x squared e to the negative x cubed plus the integral from 0 to infinity of x squared e to the negative x cubed. And I will point out, right, 0 is the typical choice, but you really could pick any number between negative infinity and infinity. Okay, so which of these do I think diverges? Good question. Well, this one here, if you think about what the function is doing, negative and plugging in the problem point, negative infinity squared is infinity. Negative infinity cubed is negative infinity, but then it's a negative infinity, which is positive infinity. So essentially here, if you're plugging in negative infinity, you're getting infinity times e to the infinity, which is big. I think that's going to diverge. On the other hand, if I plug in positive infinity here, you're getting infinity times e to the negative infinity, which is like infinity over e to the infinity. And that's going to get really, really small because e to the infinity is much, much, much bigger than just regular old infinity. So if I had to pick which one to deal with first, I would pick this piece because I think that one diverges. So if you have a choice and you think you know one diverges versus the other one, try to pick the one you think diverges because it's going to be less work for you in the end. Sometimes, though, we are faced with an integral that we cannot actually antidifferentiate. For example, the integral from 1 to infinity, or 1 to infinity, yeah, of e to the negative x squared. I think I've said this before. E to the negative x squared, e to the positive x squared are famously not antidifferentiable. We cannot find their antiderivative. So when you have something like this, one tactic is to use a comparison test. So we can use a comparison. We can maybe try to think of a function that this function is always bigger than or smaller than based on if we think it's convergent or divergent. I'm pretty sure it's convergent because 1 divided by e to the x squared, right? E to the negative x squared is equal to 1 divided by e to the positive x squared. That's something that gets small really fast, like much faster than 1 over x squared. So I'm pretty sure I think it converges. So I want to find something larger than it that is also going to be convergent, or at least something larger than I know how to antidifferentiate. Well, here's what I know. X squared is bigger than x, for x larger than 1, which we're definitely in the larger than 1 situation here. Then e to the x squared is bigger than e to the x, and 1 over e to the x squared is smaller than 1 over e to the x. And 1 over e to the x is e to the negative x, and I know how to antidifferentiate e to the negative x. So what we're going to do is we're going to instead say, well, let's look at the integral from 1 to infinity of e to the negative x. Still improper. We still have to do the usual improper things. That's going to be equal to the limit as b goes to infinity of the integral from 1 to b of e to the negative x. That's going to be, I don't know why I gave myself so little room here. The limit as b goes to infinity of the integral of e to the negative x is negative e to the negative x from 1 to b, which is going to be the limit as b goes to infinity of negative e to the negative b minus negative e to the negative 1. And then as b goes to infinity, e to the negative b goes to e to the negative infinity, which goes to 0. So you end up getting 0 plus e to the negative 1. And since this function, e to the negative x squared, is always smaller than that function, this, or let me draw a picture. There's one thing I haven't said that is important here, but wait a second. So essentially we have something like, here's the function of 1 over e to the x, which is e to the negative x. I don't know why I drew a vertical asymptote there. That is not how that function looks exactly. I'm sorry, that is kind of terrible. I'm going to draw that again because I feel not happy with my drawing there. The graph of 1 over e to the x actually looks like this starting at the point 0, 1. So there's y equal to 1 over e to the x, which is e to the negative x. And then y equal to 1 over e to the x squared gets smaller much faster, but, and importantly, is still always positive. So here's y equal to 1 over e to the x squared, which is e to the negative x squared. Always smaller than e to the negative x, but still always positive. So if the area under the curve from, I think from 1, yeah, starting at 1. So if this area under the blue curve is finite, which it is, we just showed that it was equal to 1 over e, then this area in red, which is less than the area under the blue curve, has to also be finite. So we can say that by comparison, the integral from 1 to infinity of e to the negative x squared dx must converge because the function e to the negative x squared is less than e to the negative x and still positive, and the integral from 1 to infinity of e to the negative x is indeed convergent. So that's the idea of the comparison test. That if you can't actually integrate some improper integral, you can say, well, it's smaller than the thing that's convergent, so it's also convergent. Or alternatively, it's bigger than the thing that's divergent, so it's also divergent. Being less than something that's divergent is not helpful. If the area under my curve is less than infinity, well, great. Maybe it's also infinity, or maybe it's finite. And also being larger than something that's convergent, also not helpful. Maybe I'm also finite, maybe I'm infinite. So if you're trying to show something's convergent, it has to be less than something else that's convergent. If you're trying to show something's divergent, it has to be bigger than something else that's divergent. While we don't do a whole lot of this in this class, this idea is definitely going to come back up when we talk about series and showing if a series is convergent or divergent in 21C. Let's see here. Yeah. So let's look at one more example just to kind of go the other way. So yeah, we got time. So let's say we wanted to deal with the integral from 1 to infinity of e to the x over, what do I have here? Sorry. E to the x over x squared. That's kind of gross. And I'll point out that comparing to the integral from 1 to infinity of 1 over x squared is not helpful because e to the x over x squared is bigger than 1 over x squared, and the integral from 1 to infinity of 1 over x squared is convergent. So this is exactly the situation I was just talking about. This is bigger than that, but having more area than finite area doesn't say anything definitive. So we have to figure out something else. Yeah, okay, sure, that's going to work. So it is, on the other hand, true. And this is where really you're just kind of throwing stuff against the wall. Like I'm actually looking at notes, but like really you're kind of just guessing. Well, e to the x is bigger than x. Think about their graphs. Y equals e to the x is always bigger than y equals x. But specifically, at least between 1 and infinity, that graph is certainly bigger than that graph. So then if I divide both sides by x squared, e to the x divided by x squared is bigger than x divided by x squared, which is equal to 1 over x. And we know that the integral from 1 to infinity of 1 over x is famously divergent. Right? We did it it was the first one we did in class today. It certainly diverges. And so since, or I should say, thus, the integral from 1 to infinity of e to the x over x squared dx is also divergent by comparison. because the function that we're integrating is bigger than the function we just integrated. Yeah, we have enough time. I should show you one more. There's one more example I want to show you that I think is worthwhile. Yeah. Okay. So let's say we have, I'm trying to make it work out nicely here. Let's say we have the integral of, sorry, one sec, my brain has to make it work. Negative x over 2x squared plus 3x plus 1. From 1, yeah, 1 to infinity. I really want negative x up there. That seems really wrong. I might fix it midway through. I promise it won't be that broken. So that does seem wrong. Sorry, I was trying to make it work out. So here's that. I was trying to make it a partial fractions problem first. Well, let's just so let's do the partial fractions and then we'll talk about what I really wanted here. I really feel like that's incorrect. Okay. So this is a partial fractions problem. So doing the partial fractions integral here, the denominator does factor as 2x plus 1 times x plus 1. And so doing the partial fraction decomposition, we have that negative x over 2x plus 1 times x plus 1 is equal to a over 2x plus 1 plus b over x plus 1. Oh, yeah, no, that's fine. Sorry. And then multiply both sides with the common denominator. We get negative x equal to a times x plus 1 plus b times 2x plus 1. And I feel like things are not going to work out. I hope they work. It's okay. Setting x equal to negative 1, we get negative 1 equal to a times 0 plus b times negative 2 plus 1, which is negative 1. So b is equal to negative 1. Setting x equal to negative 1/2, we get positive 1/2 on the left equal to a times negative 1/2 plus 1 plus b times 0. Interesting. So a is equal to 1. Oh, I know. I figured out what I did wrong. This is turning out how I thought it was going to turn out, but I realized I made some mistake. So do I want to fix it? I do want to fix it. So apologies for this problem. It's not quite right. Here's what here's what I wanted to happen. I wanted a to be 2. So that things worked out nicely. If a was going to be 2, this would have had to been totally different. But let's finish this problem. So here's what's going to happen. You're going to get the integral of 1 over 2x plus 1 minus 1 over x plus 1 dx. That's going to be, unfortunately, 1/2 the natural log of the opposite value of 2x plus 1 minus the natural log of the opposite value of x plus 1. And then if we actually do the improper part of this, this is going to equal the limit as b goes to infinity of our antiderivative evaluated from 1 to b. And when we plug in b here, it's actually kind of a little bit weird because you get the natural log of 2b plus 1 minus the natural log of b plus 1. That's like an infinity minus infinity, which is not very nice. It's not fully determined, but we can actually deal with it. So here's what happens. And of course, I've written this in a place where I'm going to run out of room. So let me move this over here. So plugging in, here's what we've got. We've got the limit as b goes to infinity of 1/2 the natural log of 2b plus 1 minus the natural log of b plus 1 minus 1/2 the natural log of 2 plus 1 minus the natural log of 2. Okay, so how do we deal with this when it's an infinity minus infinity? Well, in this particular case, we can combine these things together. So we can write this as the limit as b goes to infinity of the natural log of 2b plus 1 to the 1/2 power minus the natural log of b plus 1 minus, I don't really care about this over here, but it's 1/2 the natural log of 3 minus the natural log of 2. And then we can put these together using our log rules and say that this is going to be the limit as b goes to infinity of the natural log of 2b plus 1 to the 1/2, which is the square root of 2b plus 1, divided by b plus 1, minus all this. And then I think this gets a little bit weird. Yeah, it does. So this limit here, you'd have to use L'Hopital's rule, which I guess we have enough time to do, so we'll do it. So using L'Hopital's rule, we get the limit as b goes to infinity of the natural log of the derivative of the top, which is 1/2 times 2b plus 1 to the negative 1/2 times 2, divided by the derivative of the bottom, which is 1, minus all this junk over here. And then finally, we're almost there. This is the limit as b goes to infinity of the natural log of 2 times 1/2 is 1. So you have 2b plus 1 to the negative 1/2, or 1 over 2b plus 1 to the positive 1/2, minus all that over there. It's a lot of work. And then finally, b goes to infinity. 2b plus 1 goes to infinity. Infinity to the 1/2 is still infinity. 1 over infinity is 0, and the natural log of 0 is negative infinity. Undefined. So this is going to be equal to negative infinity. So this integral diverges. Now, let me point out something and then I'll stop talking. I should have known this was going to diverge from the get-go. Here's how I should have known. Looking at the original integral, if you look at the highest power of x in the numerator, you have x to the first. With the highest power of x in the denominator, you have x to the second. We essentially have an integral from 1 to infinity of x over x squared, which is essentially the integral from 1 to infinity of 1 over x, which we know is going to be divergent. So if you compare the highest powers of x in the numerator and denominator, and you get something that you know is divergent or convergent, it's a really, really good bet that the actual thing you're dealing with is also going to have the same behavior. All right, that's all I got. Good luck on your test tomorrow if you have a test tomorrow. I do, so by the way, I don't think this really matters because you're all, when is your test tomorrow? For those of you that have it? 2? Okay, well, anyway, the thing I was gonna say is I have my regular office hours in the morning tomorrow at 10 o'clock, but I won't be holding my afternoon office hours from 2:15 to 3:45, but I don't think that really will make much of a difference for any of you because you probably won't need to come to that, but they won't happen in the afternoon tomorrow. So don't expect to see me in the afternoon, but I will be around for my usual morning office hours and done. That's all. You're free to go. I mean, you're always free to go, by the way, in case you're always free to go. Thanks for hanging around.